Dear students, welcome to the third lecture on the optimal control. So, in the previous lecture we have seen the problem of finding the optimal control of 1 and 2. So, we considered the system dx by dt equal to f of x of t u of t where x is the state variable and u is the control variable, and the performance index to be minimized or maximized is given by the expression J1 which is equal to the function s x of capital T comma t plus integral t0 to capital T f of x u t dt, and here capital T is the final time and t0 is the initial time, and our aim is to minimize or maximize the expression j under the constraint given in the equation 1. So, last time we have seen the necessary condition which is the Euler-Lagrange equation is given by del L by del x minus d by dt of del L by del x dot equal to 0 and del L by del u equal to 0 is the fourth equation, and the boundary condition to solve this equation is given by the del j should be equal to 0, which is the necessary condition for the minimization or maximization problem, where del denotes the variation. The first variation of j equal to 0 is the necessary condition. So, here del j equal to 0 implies the value of L at the final time t into the variation of capital T plus del L by del x dot transpose into del x dot evaluated at final time t should be equal to 0. Here L denotes the Lagrangian function given by this expression. L is a function of x dot u and the Lagrange multiplier lambda and t, and which is given by this expression capital F function plus del s by del x transpose into x dot plus del s by del t plus lambda transpose. The Lagrange multiplier is a vector function, and so lambda is the column vector and lambda transpose is the row vector, the Lagrange multiplier, and it is multiplied by small f of x u minus x dot function. Okay. All these are evaluated at the optimum value x star u star etc. So, in general L is a function of all these variable x dot u lambda etc., and the Hamiltonian h is defined by f capital F function plus lambda dash times small f function. Therefore, the Lagrangian L in terms of the Hamiltonian h is given by this expression, which can be easily seen from the previous step. Now, the condition which was the Euler-Lagrangian equation 3 and 4, if we convert it in terms of Hamiltonian h is given by this expression del L by del u equal to 0 is same as del h by del u. From the previous expression we can easily see this one from here, and del h by del x, it should be x here, equal to minus lambda dot, that is the seventh equation. Del h by del lambda equal to x dot is the equation which is already given. Del h by del lambda we can see from here, it is nothing but this function small f. So, the equation 8 is nothing but the equation given x dot equal to small f, which is the equation 1 itself. Okay. So, already these three expressions along with the boundary condition h plus del s by del t evaluated at capital T into the variation of capital T plus del S by del x minus lambda evaluated at capital T into variation of the final position x suffix t. So, this we have not proved in the last lecture. We have to prove that the boundary condition given by 5 in terms of capital L, if we convert it into by del u equal to 0 is the fourth equation, and the boundary condition to solve this equation is given by the del j should be equal to 0, which is the necessary condition for the minimization or maximization problem, where del denotes the variation. The first variation of j equal to 0 is the necessary condition. So, here del j equal to 0 implies the value of L at the final time t into the variation of capital T plus del L by del x dot transpose into del x dot evaluated at final time t should be equal to 0. Here L denotes the Lagrangian function given by this expression. L is a function of x dot u and the Lagrange multiplier lambda and t, and which is given by this expression capital F function plus del S by del x transpose into x dot plus del S by del t plus lambda transpose. The Lagrange multiplier is a vector function, and so lambda is the column vector and lambda transpose is the row vector, the Lagrange multiplier, and it is multiplied by small f of x u minus x dot function. Okay. All these are evaluated at the optimum value x star, u star, etc. So, in general L is a function of all these variables x dot, u, lambda, etc. and the Hamiltonian H is defined by f capital F function plus lambda dash times small f function. Therefore, the Lagrangian L in terms of the Hamiltonian H is given by this expression, which can be easily seen from the previous step. Now, in the terms of capital H is given by 9. So, this we have to prove it, and we will prove it as a theorem. So, first the given condition is this one, L evaluated at capital T, this is a correction, it should be capital T into del of capital T plus del L by del x dot transpose into del x dot at evaluated at capital T, that is our condition 5. So, this condition 5 we want to show it to be equal to the condition 9. So, let us take the condition, the boundary condition in terms of L as given here. Now, we can easily see this expression del x suffix t is equal to del x of capital T plus x dot of t capital T plus del x dot of capital T into del t. So, this we can see in the following way. So, if we consider the initial condition is, let us say T naught is this one and x naught is this expression. So, that is the initial condition, and let us say this is our optimal solution x star of t, and this is the variation of this thing. So, it is x star of t plus the variation in the function x of t. Now, let us say this is the time t and this is the variation in t plus delta t, because we are the t may not be a fixed value, it also has the variation. The final position is not also a fixed value, it can have a variation. So, here this is the final position for x dot and the final position for the variation of x star plus del x star is this expression. Now, we can see here this expression, and this particular point if we take. So, this is the variation in x of capital T is this expression x suffix capital T, and the next one is x of capital T plus del x of capital T. The variation in this expression, that is different. This expression is this particular point, and there is another thing which is x suffix T plus del x suffix T. That is, the final position of x star is x suffix T, and x suffix T plus del x suffix T is the actual final position of the incremented function x star plus del x star. So, we have 3 values here, and from here we can easily see this expression. You can see that del x suffix T is equal to del x of T, the variation in x of T, plus the point A is the final position of x star, and the point B is the incremented position of the x star at capital T. That is, x of capital T is this position, and the incremented value is x plus del x of capital T, and this x suffix T is the final position, and the final position of the x plus delta x function is here. So, C this M C or Cm is nothing but x suffix T and its increment del x suffix T is given by this one. Now, we can see that approximately the tan of this angle is equal to BC is this height, and delta T is from here to here, the increment in capital T. So, BC by delta T is the tan theta, tan of this angle, but that is nothing but the slope of this curve at the capital T position. That is, x of t plus del x of t, its derivative evaluated at capital T is the slope of this tangent, and that is equal to tan theta, which is BC height by delta capital T. So, that is the expression. So, tan theta is nothing but x dot at capital T plus del x dot at capital T, and BC is nothing but del x t. From here we can see del x suffix t minus del x of capital T, and divided by del capital T is given. So, from this expression, keeping del x suffix t in one side, we get this expression del x suffix t capital T is del x of capital T plus x dot of capital T plus del x dot capital T multiplied by del capital T. Now, by neglecting the second variation del x dot of t into del t, the product of two first variation we omit, and keeping only the first variation, we get del x capital T is equal to del x suffix t, and bringing it to the left hand side we get x dot at capital T into del t, okay, approximately equal, by neglecting the second variation. So, substituting this del x of capital T in the expression of the boundary condition in the equation 10 and converting it into the h value, we will get this following expression. So, first L at capital T into del capital T is there, plus del L by del x dot into del x dot capital T. That this del x capital T, we are replacing it with this expression. So, we will get L minus del L by del x dot in transpose into x dot of capital T. From here we will get this expression. See, from here we can see that del x of capital T equal to x dot of capital T into del T, that is substituted here, plus the remaining term del L by del x dot and del x of small t is substituted here. So, we get this expression 11. And now converting L in terms of H as shown in the previous slide here, L in terms of H equation is given here, and substituting in this equation 11, we get the equation 12 here directly, because L equal to H plus del S by del X transpose etc., and del L by del X dot. From here we can see that it is nothing but del S by del X transpose plus minus lambda dashed here, okay, this from this expression. Now, L evaluated at capital T is similarly this expression L minus del L by del x dot into x dot T. If you substitute in terms of H, L evaluated at capital T minus del L by del x dot into x dot is in terms of H is given by H at capital T plus del S by del T evaluated at capital T. So, that we can see from the previous equation. So, substituting these expressions in the boundary condition, we get the equation 12. So, this is the proof that the boundary condition 5 is equivalent to the boundary condition 9 in terms of H. So, these equations will be very useful in solving various optimal control problems. For example, we consider the problem x1 dot equal to x2, x2 dot equal to minus x1 plus u. The boundary condition x1 of 0 equal to 1 and x2 of 0 is 0. So, here initial condition is given, okay. The final boundary at capital T, we will consider different cases. The performance index to be minimized is given by J, it is half x1 of capital T square plus x2 of capital T. This is the function capital S in the expression of the problem. We are considering the problem given in 1 and 2. So, S as a function of capital T, and inside the integral we have the capital F function. So, in this particular problem we consider capital F function as x1 square plus u square. The boundary conditions, the final boundary condition we consider are the following. Case 1, T is fixed, that is 5, and the final positions x1 of capital T, x2 of capital T are variables, and case 2 and case 3 are different cases. T is a variable and final positions is fixed in one case. In the second case, final position is also a variable. So, we see how to solve this optimal control problem. So, the Lagrangian function L, according to the definition, it is capital F plus this expression, and in terms of H it is the expression given here. So, in this problem H is which is capital F plus lambda dashed into small f, and we substitute capital F is x1 square plus u square, and capital S function is half x1 of capital T square plus x2 of capital T. Initial condition is 0, final time is 5, and initial boundary condition x1 of 0 is 0, x2 of 0 is 0. So, this is the first case, as given in the problem. Now we have to find the Euler-Lagrange equation, necessary condition in this following way. So H is given by this expression, a capital F plus lambda dashed into small f function is this, and the Euler-Lagrange equation is del H by del u equal to 0. So if you substitute directly del H by del u, it is 2u plus lambda 2 equal to 0. So the control u is given in terms of the Lagrange multiplier lambda 2. So u equal to minus lambda 2 by 2. So the control u is given by minus lambda 2 by 2. Now del H by del lambda is equal to x star is the second condition, but del H by del lambda is nothing but small f. From here we can see directly, which so the condition gives x dot equal to f, which is the same equation as given in the question itself in the given statement of the problem. So x dot equal to f is x dot equal to f means it is x1 dot equal to x2, x2 dot is minus x1 plus u, the given system of equation. The third Euler-Lagrange equation is lambda dot equal to minus del H by del x, or it is minus del H by del x1 and del H by del x2. So if you substitute this value using the H expression, we get lambda 1 dot equal to minus 2 x1 plus x2 plus lambda 2, lambda 2 dot equal to minus lambda 1. So we have the expression as given here. If you see the equation 14, in the place of u we can replace it with the equation 13, that is u equal to minus lambda 2 by 2. So by substituting u value here, we get x1 dot equal to x2 and x2 dot equal to minus x1 minus lambda 2 by 2. So the system 15 and 16, they are the coupled system of ordinary differential equations. So we have to solve this 4 equations, 4 first order differential equation, and the boundary conditions to solve this problem are as we have already derived, it is given in the expression. So in case 1 given by this one, t equal to 5. So it is a fixed value, there is no variation in t. So delta t equal to 0, and x1 t, x2 t are variables. So the variable boundary condition is only in the second term. Delta capital T is 0, therefore the boundary condition is given by del s by del x minus lambda t transpose evaluated at capital T should be equal to 0, because del capital T is already 0 and del x suffix t, the variation in the final condition is arbitrary. Therefore the expression into an arbitrary value equal to 0, that implies the vector given in this bracket should be equal to 0. So we get the condition del s by del x minus lambda dashed should be equal to 0 evaluated at capital T. So if we substitute s value and then differentiate with respect to x1 and x2, we get this equation, because s equation is this. So s function is nothing but half x1 square plus x2. So if you differentiate with respect to x1, we will get x1, and differentiate with respect to x2, we will get 1 here. So del s by del x1 is nothing but x1 minus lambda 1, del s by del x2 is 1 minus lambda 2, that is the 0 function. So from here we will get lambda 2 is equal to 1, lambda 2 evaluated at capital T is 1, and lambda 1 at capital T is nothing but x1 of t. So the coupled equation, 4 equation is written in the matrix form like this: x1 of x1 dot is x2, x2 dot is minus x1 minus half lambda 2, etc. As we saw in the previous thing, the 15 and 16 equations are coupled, and they can be written in the matrix form like this, and the boundary conditions is given in the problem, that is at t equal to 0, these two are already given, and these two boundary conditions are derived just in the previous slide here. So, along with these 4 boundary conditions, we can solve the system of equation in the usual way. We know that the equation x dot equal to Ax with some initial condition x of 0 equal to x 0. So, the solution is x of t small t equal to e to the power a t into x 0. So, using this form we can solve the equation, we can solve this equation, and then substituting the boundary condition we can get the solution of the problem. So, in solving this equation we will get the values of x1 of t, x2 of t, lambda 1 t, lambda 2 t. Now, after getting the value lambda 2 t, we substitute it in this equation, that is equation 13, u of t equal to minus lambda 2 by 2. So, lambda 2 of t we are solving from the system of equation, substitute here we get the control u of t, that is called the optimal control for this problem, and the solution x1 of t and x2 of t, after getting the solution with the boundary condition we call that as the optimal state of the system. x1 star, x2 star are the optimal state that is coming from the solution of this system. So, this can be solved like this. So, now we consider the second example quickly. In this case x1 dot equal to x2, x2 dot equal to u, and initial condition is x1 0 equal to 1 and x2 0 equal to 0. The function performance index to be minimized is j, which is given by x1 square at final time plus this expression. So, s of capital T is nothing but x1 square capital T by 2, and capital F function is given by u square by 2. So, these are the two things, and h is equal to capital F function plus lambda times small f function is given in the right hand side of the equation, x2 and u, this is the small f function. Now, by applying the formula Euler-Lagrange formula, the necessary condition, del h by del u equal to 0 will give u equal to minus lambda 2, and lambda dot equal to minus del h by del x, that equation gives this one, lambda 1 dot is 0, lambda 2 dot equal to minus lambda 1. By directly differentiating h with respect to x1 and x2 we get this one. So, the solution, the equation is lambda 1 dot equal to 0, lambda 2 dot equal to minus lambda 1, and then the given system of equation is x1 dot is x2 and x2 dot is u. In terms of lambda, because del h by del lambda is the equation, the two system of equation already given and converted in terms of lambda, and then lambda 1 dot lambda 2 dot equation, all the 4 is written in the form of a system like this, which can be solved easily. Now, for the boundary condition, if t is fixed and the final position is free, as we have seen in the previous example, del of capital T is 0, and so the remaining condition, if you substitute, we get the boundary condition as x1 at capital T is lambda 1 at capital T, and lambda 2 at capital T becomes 0. By differentiating the s function with respect to x1 and x2, we get this value, and lambda 1 t and lambda 2 t is given by this. So, we get the boundary condition in this form, and we have to solve the system of the 4 by 4 matrix. So, the solution can be easily obtained directly here, because lambda 1 dot equal to 0, it implies that lambda 1 is a constant, and when we substitute that constant here, lambda 2 dot is a minus constant. So, when we integrate, we will get lambda 2 is minus constant into t plus some other constant C2. So, this 2 is solved directly from here easily. So, we can substitute directly. Lambda 1 is a constant, lambda 2 is minus that constant t plus C2, and now substitute this lambda 1 lambda 2 in the equation. X2 dot is minus lambda 2, and when we substitute lambda 2 here, we get this expression C1t minus C2. So, integrating this both sides with respect to t, we get x2 of t is C1 t square by 2 minus C2 t plus C3 constant, and we are given that x1 dot is x2. So, substitute x2 in the right hand side, and then integrate, we will get x1 as the solution like this. Now, the C1, C2, C3, C4, all this can be found out by directly substituting the boundary conditions. All the conditions can be easily substituted and it can be easily solved. All the 4 constants can be obtained. So, after substituting all these constants in the expressions, so we get x1 of t is this, x2 of t is this, that is the optimal state variable of the problem, and the control is given by this expression, that is u of t is minus lambda 2, and lambda 2 is obtained by this expression, lambda 2 of t is minus C1 t plus C2. So, this is the optimal control for the given problem. So, here we have seen 2 examples in which the final time is a fixed value, okay, where the variation of final time is 0, and made use of the boundary condition accordingly. But in the next lecture we will see various other cases. The remaining 2 cases we have to discuss, the cases where final time is variable and final position are fixed, and both final time and final position both are variables. In such problem, how to find the optimal control. So, these cases we will discuss in the next lecture and solve some examples. Okay, thank you.